Okay. Good. So welcome everybody to the Tunneling in QFT online series of talks. This is the 15th of the series. And we're very happy to have Thomas Steingasser, who's a postdoc at MIT and Black Hole Initiative at Harvard University. So Thomas did his PhD in Munich, and now he's a postdoc at these institutions. And he's worked on a variety of topics, including metastability, Higgs criticality, and instantons. And I'm excited to hear this talk today because he'll be talking about steadyon picture of excited state tunneling. So if you're interested in this, if you're new to this series, then check out the YouTube channel for previous talks. And I should just mention that the next one is going to be on May 22nd. That's going to be Matthew Johnson. So for today, Thomas, please take it away.
Okay, so thank you for caring about my research so much. Yeah, so I will talk about a new framework that we came up with that we hope will allow us and all of us to describe tunneling out of excited states in a very nice, efficient, semi-classical way, similar to instantons coming out of a false vacuum. This should basically allow us to keep all the features that we have from that framework and just generalize them to arbitrary initial states. And to get started, I will first so to understand that framework and why we had to come up with that framework and why it's actually somewhat non-trivial, we first have to remind ourselves, why do we care about imaginary time in quantum tunneling? And one very simple way to think about it, that I personally like very much, is the so-called direct approach to tunneling, where you basically define the tunneling rate in terms of a flow of probability, right? So you have for example, here we have some potential. We have here a false vacuum. We have some little basin surrounding the false vacuum in which the particle can be trapped. Then on the other side, we have this kind of like abyss where the particle can tunnel into and then just develop some runaway behavior. And one way of defining the tunneling rate would be to choose an ansatz for the probability that you find the particle at a given time t in this false vacuum basin. Choose this ansatz and then simply define this exponent as the tunneling rate. By the way, can you see my pointer?
Yes, we can.
Yeah.
Perfect. Okay. And okay, so far, this is all super trivial. And it is also very trivial to simply solve this equation for this tunneling rate gamma, right? It's just take a derivative, you do some rearrangement, and then you use that whatever you lose in probability here, you gain in probability on the other side. And then you get this extremely simple looking equation. Okay, how can we relate that to path integrals, to instantons, to all the things that we know, and then ultimately generalize it? So the way to do that is to acknowledge that, to observe that we can take this probability and express it in terms of, for example, a trace over the density matrix, or if you don't like density matrices, simply wave function absolute value squared integrated over the region that we care about. And okay, so far this is all very simple, but now what we have here are, of course, propagators. And we can then take these propagators, rewrite them in terms of path integrals, do a lot of algebra to take care of this derivative. And once you do that, you get something that looks now very hard to follow, but I will explain it in detail because I will rely on it. But in essence, what you get is a product of two path integrals, some normalization factor. And if you look a bit closer, as you see here, these are just path integrals from our false vacuum that we're tunneling out over here to some other position that has the same energy. Okay, here the e to the is, you all know what it is. this weird looking object here is simply a functional delta that only chooses paths that end up here at whatever time we care about the tunneling rate. So for our purpose, and if we only care about the leading order for the exponents, which is what I will talk about in the next hour, all this does is it chooses certain paths, or to be more precise, it eliminates a bunch of paths that are not the instanton that we care about, that we know about. And over here, that's just the same path integral again without this constraint. And yeah, now we're getting a bit closer to what you already know. Okay, because what we can then do is basically take these two path integrals, Wick-rotate, and then you see this will give you e to the minus Euclidean action of the path that goes from the false vacuum to the other side, bounces back. So this is the bounce that you all know. Okay, so far this is all still the coming out of a false vacuum, and you will see in a few minutes why this is super important for excited states. Now, as I said, we know for the false vacuum, by the way, interrupt me anytime if you have questions. Okay, so for the false vacuum, the tunneling rate is simply e to the minus Euclidean action of this bounce solution. And as you all know and have probably seen a million times, this bounce solution has this nice feature that it kind of, if once we rearrange everything in a nice way, we start out over, we can represent it as a solution that starts out over here at minus infinity, comes over here, reaches the touches the false vacuum, and then bounces back asymptotic, the other way around. So we start here asymptotically, come here to the exit point on the other side, bounce back, and then asymptotically return to the false vacuum. Now, why do we have this infinitely long Euclidean time interval? Where does this come from? You will see in a minute that this will teach us a lot. In this framework, if you remember, this parameter t here is the physical time. And normally when one does these computations, we assume the time to be quote unquote infinite, meaning a lot larger than like the typical timescales of the system. Because you can imagine if you start with some super localized wave package in the false vacuum, in the beginning, for like some order one time in units of the system, there will be some sort of sloshing behavior, right? You have your little package, it first has to spread out, it's going to bounce back a bit. And only after a relatively long time, we will actually get into this nice exponential tunneling regime. So really, you can think of this infinite Euclidean time as a representation of considering the process after an infinitely long physical time. Infinite in the sense of a limit. Okay, and so far this all makes sense. Everything is super clear. And now we can try to think about how this would look like if you were to come out of an excited state. And when I mean excited state, I mean for the purpose of this talk and the paper, we still start from a position eigenstate, but not the false vacuum, but somewhere up here, this little barrier. Okay, and we can try to guess naively what we would expect. So naively, what we could expect based on, assuming that everything in the derivation kind of goes through the same, would still be something that looks like the exponent, or like e to the minus Euclidean action of some bounce-like configuration. So we start again in our initial state, roll over here, roll back. And the first thing we can observe here, just if you imagine you let a point particle, you place a point particle here, you let it roll, it comes back. This will always happen in some finite Euclidean time interval. And because in the coming out of the false vacuum, what allowed for this infinitely long Euclidean time interval was the fact that we came out of a minimum, which if you flip the potential, gives you a maximum, and you can kind of asymptote towards that. Now that's no longer the case, but we have just established, and I just tried to convince you, that the infinitely long imaginary time interval is actually a manifestation of taking a physical time limit and then Wick-rotating that. So that would then suggest that actually, if we want to use a solution like that, we would have to consider an infinitely long time interval, which, first of all, if you look at it, is immediately counterintuitive, right? Because suddenly our particle just tunnels tunnels back and forth or rolls back and forth an infinite number of times. And where you see it maybe the clearest is if you imagine you don't start out of the false vacuum, but just a tiny infinitesimal deviation away from it. Right? You would expect that you basically get one nice bounce that resembles what you know from the false vacuum. But actually, right, if you take seriously this infinite imaginary time interval, you would still get something that just oscillates like crazy. And what's even worse is that this would just give you an infinite Euclidean action. So why does this not work? Why is this inconsistent? At which point does this thing that I not actually explained to you but showed you before breaks down? The point where it breaks down is the Wick-rotation. And if you think about it for a minute, you will see that actually this makes a lot of sense, right? Because when you Wick-rotate, you take you imagine your real-time axis in those path integrals, and you take the asymptotic state and Wick-rotate it. And if you come out of a false vacuum, that makes perfect sense, and that's plausible because you have first of all, you have a clear asymptotic state, and that asymptotic state has no action whatsoever. So when you Wick-rotate it and you add a little arc, that just doesn't contribute anything. However, if you come out of an excited state, right, first of all, we don't really have some asymptotic state at t going to plus minus infinity. Because if you imagine you have your particle here, it's just going to oscillate. It's rolling back and forth. And on a more technical level, that then of course implies that once you start Wick-rotating, your arc will contribute something to the total Euclidean action. So what this suggests is that we cannot Wick-rotate. As I said, we want to maybe try to keep all of the nice features of the instanton, which mostly means having a nice Euclidean time picture, but we cannot Wick-rotate. So that's the problem. And is this clear so far? Because I'm about to talk spend the rest of this talk about talking about how this can be solved. So, okay, I don't see you. I assume it's clear. Tell me if it's not. Okay, so yeah, how can we address this? So to address this, we go back to this not super nice looking formula that we had before. And okay, remember again, here's some normalization factors. These are the two path integrals that give the e to the minus se, and here just some constraint. Now, as I said, we cannot Wick-rotate, but we also obviously cannot evaluate these path integrals just in real time, because at least I don't know how to do this. But what we can do is some sort of quote-unquote compromise, which is we can keep these path integrals in real time, but regularize them. And we regularize them by taking the Hamiltonian and giving it a small infinitesimal part. Right? If you know QFT, you will agree that this is a reasonable thing to do, that we actually do all the time. Now, and what this then does, if you take seriously that you always actually implicitly have this 1 minus I epsilon, you can try to take these path integrals and again evaluate them through some sort of semi-classical expansion. In this case, it's of course not a saddle point, but it's a stationary phase because these are oscillatory integrals. But you can still do it, right? You just take the action, you find the equation of motion. And once you do that with this I epsilon, and again, you just stick to it, what you will find is that actually your equation of motion should be complex. I use this I epsilon here. So when you go through all of the derivations, you just find a equation of motion that has an I epsilon here, which then immediately implies that even if you start out from just some nice real position value, you will have a solution with complex values along the way. And that is, of course, different from what you know from tunneling out of the false vacuum. But okay, in principle, you can do it, and I will explain to you in a minute why this makes sense. But basically, this suggests we have to think about complex solutions. What it also tells us right away is if you take seriously that you need complex solutions and find a way to deal with them, you can still express your tunneling rate in this nice familiar form, where you basically get exponent of not the Euclidean action, but the imaginary part of the action of whatever solution you find for these path integrals. And then over here, a separate factor that I will discuss in the end, which comes out of this normalization. But for now, what matters is this here looks vaguely similar to the nice Coleman formula. Okay, now, why are there complex solutions? How can we make sense of complex solutions? Does any of this make sense? So to convince you that this makes sense, let me show you something that you've also seen a million times, which is simple double wave potential. Okay, consider the double wave potential. And we can now, because we don't fully understand the excited state tunneling yet, so let's go back to something that we all understand and agree on, which is if you have this potential and you start in one of its ground states, you can write down something that looks like an instanton, which is this tunch here. Okay, so far this is all very basic. You all believe me. And
Sorry, can I just ask?
Yeah.
You said start in one of its ground states. Do you mean like the global
in-
ground state where it's mixed between the two wells, potential wells, or you mean localized around one of the wells?
I meant localized in one of the wells.
Okay, thanks.
Classical ground states, yes. Okay. And as I said, we all agree we have this tunch. That's a thing, that's a good solution. But I also told you before that we can think of imaginary time in this particular framework. Okay, we can always think about it, but in this particular framework, the imaginary time really emerges as a Wick-rotation of physical time. That suggests that in principle, we can take this solution and start Wick-rotating it back, right? Because we can just do that. And what you then find is that this nice, simple tunch solution in imaginary time that you all know actually has a representation in terms of some very crazy looking complex solution. Right? So here, this is Wick-rotated relatively close to the real time axis. And again, you can just take the tunch Wick-rotated. And what we get is a complex solution that has a real part that starts out at the right initial point, so minus x0, then undergoes some crazy oscillations, then jumps to the other side of the double well, then undergoes the same oscillations but dampened, and in the end arrives where it should arrive. Another nice feature is that the enveloping function of this is actually the tunch. And we also have an imaginary part because it's a complex function now. And this solution exists. And if you go ahead and compute the tunneling rate using this slightly rearranged ordering of actions, what you get is that the tunneling rate is exactly the same as it was in imaginary time, which again makes perfect sense, right? We have an analytical solution, we just Wick-rotate it, so the result should always be the same. So what this tells us is that already in real time, already when tunneling out of a quote-unquote false vacuum, even though these are two degenerate vacua, but even for tunneling out of a quote-unquote false vacuum, we can actually, the solutions that you are used to, that all of us were used to, are just a special case of these more complex solutions defined on a complex time domain. And okay, you can then take this and you can take this further, you can get closer and closer to the real-time axis. And what you find is just more and more insane oscillations, but at the end of the day, right, in the right limit of time going to infinity, you always match the right boundary conditions and reproduce the tunneling rate that you got straightforwardly by just using Euclidean time. Okay. And this is nice because it tells us now that what I told you before about the excited states could make sense. there's a chance that looking at these complex solutions could actually work for excited states as well. Now,
Sorry, Thomas, what are you subtracting in the end? What is your z bar that you're subtracting on the previous slide?
I will explain this in the end, but to give you a spoiler, so here we have, right, these are path integrals, they have to be normalized. So here is some normalization factor that, again, I will show you in the end, is also a path integral. And that path integral we can also evaluate using this machinery that I'm about to explain.
But
Are you satisfied?
well, yeah, so on the bottom right, you have this z bar, right?
Yes.
So what is this in the case of the double well?
In the case of the double well, that's just 0.
Okay,
Because
yeah, that's what I would imagine. And when you go to an excited state, this would be a non-zero.
Yes, exactly.
Okay, good. That perfectly answers. Thank you.
Okay, great. Okay, now, let's go back to the double well. And now we can think about excited state. Okay, and to make everything a bit easier to follow, we can, we scale a few parameters, basically use this much simpler dimensionless potential. And then, if you remember, we had this, I had told you that by taking this regularized real-time action and looking for the stationary phase, we get essentially an equation of motion that's now complex, which suggests immediately that our solution will also be complex. And to take care of that, we can right away decompose it in real and imaginary part. And for the real and imaginary part, we will get two separate equations. Okay, you probably have no idea what any of this means. So let me point out some features. So first of all, here, this is, if you look up here, what you would expect for the equation of motion if it was just a classical particle, right? Forget about all the complex stuff, but if you just take the real action, take just the real part of the point particle, that should undergo just its normal classical motion. And that in this double well potential is, of course, some sort of oscillatory motion with some real period delta t. Now, that's what stands here. Then we also get a bunch of extra terms. Right? Here we have something that mixes the real and imaginary part. And also over here the same imaginary part. Okay, and here's this epsilon. So that looks like there's now an interaction term. And that, of course, also makes sense, right? Because if you imagine we took our nice real point particle, complexified it, but our potential still is some analytical function of x. So there will be terms in the potential that mix real and imaginary part. And that is what you see over here. And then down here, as I said, we have the imaginary part now. That one also gets an equation of motion. So you can think of it really as some sort of new degree of freedom. It's of course not a new degree of freedom, it's just an artificial thing that we introduced along the way. Think of it like a ghost. But basically what happens once you complexify is that instead of having just point particle and classical potential, you suddenly get something that looks like it has 2 degrees of freedom that interact with each other. And that will ultimately allow us to describe tunneling, because obviously if we would just have the classical equation of motion, there would be no tunneling. Okay, so that's the setup. And let's try to understand what this means and how we can make sense of this, because it looks very nasty, but it's actually super simple in its structure. So here I rewrote it. And okay, here's the double. That all what we can do is we can take, what matters conceptually about these very complex saddle point equations is that we can write them like this, right? So the equation of motion for the real part is classical equation of motion plus some interaction term that scales with the imaginary part. Then over here for the imaginary part, that one just has some sort of equation of motion. Now, let's go back to this kind of crazy solution that we saw before also for the ground state. for the false vacuum, and try to see, just by looking at these equations, what we would expect to get for the excited state. Okay, so imagine our point particle starts out here. Then we know that our equation of motion is, okay, imaginary part dot dot is proportional to the imaginary part. The imaginary part in the beginning is 0, because the particle does sit in a real position. And over here, the kind of sourcing of this imaginary part is suppressed by our regularization parameter, which we always assume to be small and take to 0 in the end. But for now, we keep it non-zero, but small. So that means that in the beginning, our imaginary part is 0 and will, for the first period of time, stay very, very small. That then means that, of course, the imaginary part over here, which is the same imaginary part, is 0, so there is no sourcing, there is no interaction, and our real part just undergoes its nice, usual classical oscillatory motion. So we start out here, and the real part will just start oscillating. The imaginary part stays basically 0, and if you look over here, that's what you get here in the beginning. Right, so more or less unbounded oscillation of the real part. Imaginary part is 0, undergoes some small wiggles, but with time, because of this interaction term here, the real part will start sourcing the imaginary part. And what's happening when you just solve the equations is that as the real part keeps oscillating, the imaginary part also starts oscillating, and those two oscillations source each other. Right? So the difference to just the classical, that's really the difference to just having a classical equation, is that this imaginary part kind of kicks the real part, which then starts oscillating more and more. So here it just oscillates more and more. And at some point, this oscillation has been sourced enough for it to go over the barrier. That's what's happening here. And then the same dynamics just unfolds backwards. So basically, yeah, the same thing happens backwards in the other way. And after some sufficiently long physical time, what happens is that you find the point particle, or the real part, reaches this point here. The imaginary part vanishes again. And those are exactly the kind of boundary conditions that we would have expected to describe this tunneling process in this semi-classical picture. And because this does the same thing as an instanton, but it takes a very long physical time, we've called it a steadyon, because going steadily, not instantaneously. Okay. And yeah, so steadyon, that was also in the title, really just refers to these sort of complex solutions that we can also use for excited states. Okay, so that's pretty great, because now we have we had before already a very familiar looking equation for the tunneling rate. All we needed was some sort of stationary phase. Now we have a stationary phase. We know that it actually makes sense and has this very nice physical interpretation. And now we can try to understand this a bit better. Now, the first thing is that if you remember, okay, I showed you in the beginning that in this particular framework, we defined the tunneling rate is defined through this ansatz for the loss of probability. And for if you imagine sitting in the false vacuum, the wave function is a little Gaussian, or if you want to think semi-classically, your point particle kind of just sits still, and the probability just continuously leaks through the barrier without anything happening. So you always have this kind of exponential behavior once this initial sloshing is over. Now, for an excited state, you can see very quickly that that's not what you would expect. What you would expect is that you still have some sort of exponential loss of probability, but that it's not continuous, that it's not happening continuously. So imagine here our point particle as this super localized wave package. this is an actual simulation that one of the students I work with ran for me. And basically, okay, we have our point particle slash super localized, more or less coherent wave package. You start out here. Then what you can imagine happens is while we're sitting over here, while we're kind of the closest to the top of the barrier, we will lose some probability. And that loss of probability should be exponential. So essentially, this black curve here, the wave package, splits in two. One little piece of it goes over here. This is highly idealized, by the way. So, but yeah, one part of the wave function kind of jumps through the barrier, goes on the other side. The other part is just reflected and moves over here. That gives this red contour here. Then on the other side, it's again reflected, moves over here. Again, we have now a smaller wave package. That smaller wave package also splits. We lose some probability over here, but most of the wave package is reflected. And what you can show is that the time of this oscillation should agree with just the classical oscillation time. And that means then that this ansatz that I have shown you before actually only makes sense when the physical time is a multiple of this classical oscillation time. And what makes this so nice, and actually the way we realize this is because the steadyons told us so, is that actually when you look at these steadyon solutions, this comes out automatically and necessarily because these solutions only exist when this condition is true. Now, let me show you what you missed before, maybe. Right? So you see here, the real part has these, seems to oscillate with always the same oscillation frequency. And that is exactly this kind of classical turning time, which for this potential is the same as how long it takes this super localized coherent wave package to oscillate back and forth. And what you also see is that the imaginary part is always only then close to zero when the real part is kind of here touching the imaginary time solution, but is touching this enveloping function. And only over here, basically the imaginary part is zero and the real part is pretty much exactly where it should come out. So that is very nice. Right? Because in principle, if the only condition that we had would be we come out over here, we could also try to look for solutions that end on this, that ends over here or here or here. But in those places, the imaginary part is non-zero, pretty large, so not the right boundary condition. And yeah, that's how this condition is implemented, and very reassuring that this comes out. Now, then now we know that these solutions exist, they make sense, and when they make sense. And as I said, we have simulations now, it all works out. And now we know we have the solutions and we can try to relate them to the action. Right? Because in the false vacuum case, it was pretty easy because we just did a Wick-rotation, everything was simple. Now we have this imaginary part here. And to understand how we can relate this to something that looks even more familiar, which is a Euclidean action, we can look back at this regularization that I pitched you in the beginning. And now for this potential that I showed you, that's a very simple time-independent system. So what we have fundamentally when you go, if you rewrite it in terms of time evolution operators, is always some combination of H and T, because that's a time evolution operator. That's how the Hamiltonian enters in this in the first place. And you can then do this very complicated computation. Took us a long time. We basically acknowledge that H times 1 minus I epsilon T is the same as H times 1 minus I epsilon T. So for a time-independent system, this regularization that we introduced is equivalent to just doing an infinitesimal Wick-rotation, where again, in the end, we have to take the limit epsilon back to 0 to avoid all the problems I told you about in the motivational part. But in essence, that is what we do. And that then allows us to look at our action and do the following argument, give the following argument. So this steadyon here is a solution that is defined on this diagonal contour. I've exaggerated the epsilon here. And what we want to compute is the imaginary part of the action of this analytical solution along this contour. But because we know that we know what the steadyon looks like, because we can just solve the equation, we know that it has no poles. It's a very nice regular function in this entire part of complex time space. So we can take this diagonal contour and deform it. So we can deform it into one part that goes along the real-time axis. So in a sense, we just let the particle evolve in real time until the time of tunneling, quote unquote. And because the equation of motion of this steadyon is just a slightly Wick-rotated equation of motion, or just a slightly Wick-rotated version of the real-time equation of motion, once you take the steadyon and restrict and kind of move it back up, or analytically extend it back up onto the real axis, as I noted before, you just get the classical equation of motion. So the steadyon projected up here is just the particle doing its nice classical oscillatory motion. But that is a perfectly real process. The action of that is absolutely real. So up here, you don't get any contributions to the imaginary part. So obviously the imaginary part has to come from this little branch here. And on this branch, see, again, because all of these things are related by Wick-rotation. So over here, the equation of the steadyon is, or the projection of the steadyon onto this imaginary time axis solves the Euclidean equations of motion. And that then is something that looks very much like an instanton, right? You have the Euclidean equation of motion, you have the solution of it, and you compute its Euclidean action. That's what the action looks like on this little piece here. So what this tells us is that whenever we can do this and actually hit the right boundary conditions, we come out at something that looks like an instanton, quote unquote, but defined on a finite imaginary time interval. But a finite imaginary time interval really comes out of this condition that physical time times our regularization parameter gives us this little offset here, which makes the whole thing depending on the regularization parameter, and I will explain that later on. But for now, this is nice because it gives us this very simple picture that essentially this imaginary part of this complex solution that is super well defined will be the same as the Euclidean action of some Euclidean solution, which I've indicated here as this little enveloping function again. And this also then kind of, okay, in using this picture, if you look at the paper where it's in more detail, because I have only finite amount of time, but basically, and this picture then reveals how to make sense of this infinite time limit. Because you will see that this solution here for any finite epsilon does not actually hit the right boundary conditions, but only up to some deviation that is of order epsilon. But then by taking simultaneously the limit of epsilon going to 0 and t to infinity, you can actually arrive at the right boundary conditions. Okay, and that's great because we're getting closer to something simpler. Okay, that's what I just said. Now, okay, so basically now we've taken care of now we've taken our magical formula, and I've shown you that we can evaluate these two path integrals together with some massaging, with some algebra, with some complex analysis. We can rewrite them as something that's just e to the minus Euclidean action of some solution. And we get, okay, that solution has more subtleties that I will explain in a bit. Now to answer finally the question from before, what is that everything we have to take care of? Is that everything we have to worry about? No. because we have also this normalization factor, right? That's inevitable for any path integral, which is also a path integral. And you can also rewrite that normalization factor in a very similar form, right? So you can write it as a path integral where you go from xi to some outcoming state and go to some outgoing position, and then from that some outgoing position back to xi. And in the case where you come out of a ground state false vacuum, right, you could simply use a constant solution here. Right? If you look back at the double well, if your initial state is x minus, and you're computing this normalization factor, you would, the simplest thing to do and the other thing to do is just choose as a solution x is the x false vacuum, right? Because that's also, if you care a lot about prefactors, you always have this extra factor that gives you this determinant that you need to keep everything finite. That comes out of this path integral, and for false vacuum tunneling, it's just a constant solution. But if you start out from some excited state, so position eigenstate, then obviously you cannot just have a constant solution. And that means that this normalization factor will now be something that's not just one, but actually this particular path integral expression here. And again, that seems to have all of the problems that we had before when we tried to find an instanton, which is we cannot just Wick-rotate, it's not super simple. But we also just developed a machinery to evaluate these kinds of path integrals. And we can use that here. We can apply that here. And what you then get are, again, funky looking complex solutions that have an imaginary part, that have a real part. And okay, they looked, if you know about the shot solution, or just to explain the terminology, for the false vacuum, in the context of false vacuum tunneling, people introduced something called the shot solution. And this solution looks somewhat similar, which is why we called the real-time, this complex solution that takes place of the steadyon, called it a drag, because a drag is a slow pull. And once you then again go through all of the complex analysis magic, you again find that you can take this imaginary part and rewrite it as the Euclidean action of some complex time solution that appears as the enveloping function of the real part of this complex solution. And that one we called the pull, because that's kind of, it looks like the shot, but in the opposite direction. So pull, and a drag is a slow pull, because it again takes a long time. But basically what I was trying to say, what actually matters besides the funny naming, is that also this normalization factor can be dealt with using this extremely simple complex solution picture. And as I also said, one benefit of this analysis and using these path integrals and starting from first principles is that you're actually sensitive to this factor. Because in general, that factor is non-zero. Okay, and to show you that it actually matters, or how much it matters, okay, this is the Euclidean action of the quote-unquote instanton for this double well potential. Here's our initial position. Okay, and right, so here, this is at -1. Up here is 0. And what you see is if you only look at the instanton, okay, if you start tunneling at the top of the barrier, obviously you have no suppression. That makes perfect sense. Down here, if you get all the way into the false vacuum, you recover just the classical generic Coleman instanton. That also makes a lot of sense. But for those intermediate positions, you actually get a somewhat significant contribution from the normalization factor. So it's like more than 20-ish% in the region where it's the most significant. And if you sum them up, you notice that the Euclidean action in that particular regime, or the effective Euclidean action, or just the overall exponent, has this little dip here. And yeah, that is very nice. Now, another thing that comes up, now we're reaching my buffer slides, but they're also very interesting. Okay, another immediate question that you could ask, or that you probably would ask if you would let this ferment in your brain a bit, is I have just shown you that once you deal with these excited states, we are suddenly dealing with finite imaginary time intervals. Now, having a finite imaginary time interval also affects how we think about initial velocities. Because when you go back to the false vacuum, the intuition you have there, it makes perfect sense that you consider as initial position 0 velocity, because you want to match the boundary condition after an infinite imaginary time. And really the only way to get on the barrier, okay, but if you imagine you're trying to roll here in the inverse potential on top of this local maximum that represents the false vacuum, the only way to do it is if you have 0 momentum. Because if you have finite momentum, you will just kind of shoot over it and reach it after a finite amount of time, finite amount of Euclidean time. But now, okay, that, yeah, basically sets the initial condition. But now, because we have understood we can actually worry about finite imaginary time intervals, that also tells us that this no longer prevents us from having an initial velocity. So that means that when you integrate over your saddle points, when you go back to the kind of stationary phase expansion, you do not only get one unique stationary phase, you get an infinite number of stationary phases, each of them representing a different initial velocity of this steadyon. So what you have to do is you have to integrate over all of them, and at some point, okay, what you can then do is you just have all these you have all these steadyons, all of them contributing something to the exponent, and for practical purposes, that means you just compute the solution for any given velocity, compare them, and you will find that one of them is less exponentially suppressed than the others. And funnily, that happens to be the one that's just a section of the kind of, in this case, Tange instanton describing the false vacuum time. And another thing, in case you don't care about excited state tunneling, but mostly false vacuum, in principle, you can do the same for false vacuum tunneling, right? Because we have now established that finite imaginary time intervals are okay, but you will find that actually all those solutions with finite momentum are just more exponentially suppressed. And okay, so that, if you put it all together, sets up a more or less coherent and self-contained way for computing, at least to leading order for now, the tunneling rate out of some quote-unquote excited state, where by excited state, I always meant a position eigenstate. And you all know a position eigenstate is not a good physical state. So can we actually generalize this to deal with actual physical states? And the answer is yes. And the simplest example, and ironically, it doesn't seem like the simplest example for how one can apply this, is tunneling at finite temperature. Because if you go back through the literature on finite temperature tunneling, you will find that, first of all, the tunneling rate, if you really care about quantum tunneling, has not been derived properly out of first principles ever. Like, there are some analogy-based arguments, but they all rely on other computations that have since been proven wrong or incomplete. If you think about classical transitions, everything's fine, everything's rigorous, but really first principle tunneling out of finite temperature at finite temperature never been done. But obviously it's very important to have that, because right, with all these bubble nucleation, gravitational wave experiments coming up, it would be nice to have some precision there. But to have precision, you need to know what you actually have to compute, preferably beyond just using an analogy, but actually having some non-perturbative path integral. But for that, you need a first principles derivation. Then also all of the kind of analogy-based arguments always assume some sort of, static finite temperature system. But obviously this is not a static system, right? Because of the tunneling, we are losing probability. So it's not static, things are happening. Then we also have this funny question that we actually seem to get two time scales, right? We have the physical time and we get the little imaginary time excursion corresponding to the inverse temperature of the system, e to the minus beta h. And together, these two last things suggest that we actually should compute the tunneling rate on something that looks more like a Keltisch Schwinger contour. I hope you know what it is, which is very different from this kind of naive guess that people like to use where they just impose periodic boundary conditions and imaginary time. No, this is fundamentally a complex time contour problem that needs to be solved. And also a minor issue, but how does one even define finite temperature in a false vacuum? Because it's not thermalized. Okay. And good, I have 5 minutes left. That's actually enough. So how can we apply this fancy new framework to deal with this somewhat old problem? Okay. So first of all, this is how I imagine a finite temperature system. Note that I have transitioned to fields because we wrote this paper for fields. Okay. So here we have some barrier protecting our false vacuum, and a finite temperature system would mean that we have a density matrix describing the system that looks like e to the minus beta h, beta being 1 over temperature. But as I also said, this system should not be thermalized. So what we considered was this very much over idealized supercool state, where we basically have an e to the minus beta h distribution within this false vacuum basin, and at t equals 0, no support over here in this part of field space. Okay. Now, why is this the simplest system to deal with? In this new framework, take this, to see that we can take this e to the minus beta h and simply take this matrix element here that we care about. Because if you remember, in the very, very beginning, I defined the tunneling rate through probabilities, which are traces over density matrices. And what you can see now is that I can take this density matrix and then do this insultingly trivial thing, which is insert an identity to bring it to this particular form here. And then we can observe that before, for the point particle, this very same probability looked like this. Right? And now you compare the two and you see, this xi here is phi star, because here I integrate over that, but fine. So this is formally the same. And here we always had this time evolved state that we're tracing over. Now here we have state that we're tracing over and a Euclidean time evolution operator. So it's pretty much the same structure. And that's nice because it allows us to actually do this computation in a very simple way. And okay, how can you visualize this? Well, we can visualize it like this. You get essentially you get the Keltisch Schwinger contour, because here this e to the minus beta 1h, e to the minus beta 2h, that is the same as a imaginary time evolution. Then we also have the physical time, so we also have to time evolve these states in physical time. That then gives us these two legs. And then we basically have something that's formal. Again, it's hard to explain how similar this is. It's exactly the same problem that we solved before, because we now again have some e to the is of some complex solution. We can solve those equations, and in particular, we can solve them on this diagonal contour, because I now showed you the dynamics, and you know that nothing in this dynamics can become singular. Everything has to be nice and regular at least in this little rectangle on the complex plane. And this is take the okay, we can solve this. We can find a solution along this diagonal contour that's basically a steadyon and can move that however we want in the complex plane because everything is regular, because we know what the solution looks like and we understand it. So we can essentially move it onto this contour here, doing exactly the same argument as before. Up here, we get no contribution. Down here, we get no contribution in the limit of a very large physical time. Here we have the imaginary part. And you also see that anyways, letter. And basically by putting it all together, what you end up finding is that indeed, if you tunnel out of the supercool state and take the limit of a very large physical time, that's important, then you recover essentially a periodic instanton, which I think the first paper in which I saw it was by Linde in 81, where he basically just wrote, obviously it has to be this. Yes, it makes sense, but now we understand why. And as I said, it really only works in this limit of a very large physical time. And yeah, in any case, this is first principles. And what was hopefully not obvious to Linde is how to write down the full path integral and go beyond this leading order expansion, which we now can in principle do because we know what to evaluate. Okay, let me summarize. Okay, I will just take 1 more minute. Yeah, so what I wanted to convey and what I hope that you all got, if you didn't, I will repeat it now, is all these little computations that we do for tunneling where we use imaginary time, Euclidean time, that's actually more subtle than one would think, especially when going to excited states. I was surprised by how non-trivial all of this became. But even though it's very complicated, we can actually deal with it in this extremely simple way of just regularizing it a bit, understanding keeping in mind a few conceptual subtleties. But in principle, this new method of infinitesimally Wick-rotating versus doing the full Wick-rotation has proven super powerful. It has worked here. If you like to study semi-classical solutions, there's an entirely new classes of nice semi-classical solutions that you can study that are super important. All of this has this, and this is I think what I found the most shocking when figuring all of this out myself. All of this has this super, super simple, nice, intuitive interpretation, but literally of just 2 point particles oscillating and kicking each other. Similar for fields. I did not talk about fields. And maybe the most consequential aspect of all of this is that I showed you 2 kinds of path integrals that we evaluated in exactly the same way using this method. But in principle, this is not restricted to tunneling problems. But you can do the exact same thing with any boundary conditions. That's why I was so happy about the normalization factor, because that one has different boundary conditions and it can still be dealt with in this way. And of course, all of this was just for a position eigenstate. There's a lot of work left to do to, do energy eigenstates. We're on that. Do general fields are also looking well. We still have to figure out functional determinants. But in principle, all of this is super reliable because the derivation that I showed you, or the kind of starting point of my derivation, is super simple. It's all first principle. We understand everything that goes into this. And yeah, I hope that it may help one of you with one of your problems. Okay. Question, if there's time.
Okay. Thank you.
Ah.
It's a nice presentation. I think we have the first question by Ian. So go ahead.
Oh, hello. Can you hear me okay?
Hello. Yes.
Thank you. That is a very clear talk. I suppose one comment and one question. There's quite a lot of literature on complex paths. I'm sure you're aware.
Yes.
I think Carl Bender is a person who's been promoting complex paths the longest. And he's produced a review last year. I suppose I think I get the impression that what you've done that beyond Bender's work is to consider more the excited state as the initial configuration. And also a follow-up question you can answer at the same time, and that's for the double well you're talking about, I will be concerned about recurrences. You know, in that system, you always have the possibility, well, you always have the certainty that the particle will tunnel back. And how do you avoid, and do you see that? It's two questions.
Yes. So that's a very good question. So in the beginning, when I skipped a lot of very tedious path integral algebra to get to this magical formula, one of the things I skipped here was the point where one assumes no back tunneling. If you want to allow for back tunneling, that is something you can take into account, but it will give you a slightly different path integral expression. So basically, this delta here encodes the information that we only consider one instance of tunneling. But yeah, there is a more complicated version of this that takes into account like one back tunneling, two back tunnelings, etc. So, but that's why we don't see it in the semi-classical solution, because we already filter it out before. But for each of these path integrals, it should be pretty straightforward to just do the same with modified boundary conditions.
More questions? A naive question. So in quantum mechanics, if you are tunneling, if you're hitting a barrier, there are certain momenta that give you a higher probability of tunneling, like a resonant enhancement. Do you see that in your analysis if you choose a particular xi to get an enhancement, like a resonant tunneling in this case?
So for this particular double well, I showed you the. So we do have a momentum dependence. Right? Well, okay, it's a bit tricky because we're dealing with a position eigenstate. So you kind of have all of the momenta in there simultaneously. If you Fourier transform this, you just get this flat momentum distribution. So we do cut out the momenta that will just classically transition over. And for the other ones, we get this set kind of very simple Euclidean. We get the dependence on the momentum, but of course not on a momentum in the sense of we're dealing with a momentum eigenstate, which you may have in mind, because these are position eigenstates.
I see.
Because you can build momentum eigenstates out of these, or like approximate momentum eigenstates. That's what is one of the things that are currently happening. But yeah, maybe you see it, maybe you don't. I don't know yet.
Okay, yeah, thank you.
I would hope that we do, because otherwise that would be concerning.
It would make sense if you see.
Yeah.
Okay. Good. There's another question by Ian. Yeah, Ian, go ahead.
I'm sorry, I only put my hand up because I wanted to make a comment and just know. I mean, I'm very happy if anyone else wants to jump in and ask questions. I don't want to monopolize anything. This is just an observation that I find kind of interesting that I think it's not widely known. When you do the instanton, it starts off right at the bottom of the potential in the false vacuum, whereas tunneling from the ground state is not, it's got some false vacuum energy above the ground state. Now, the kind of interesting point is that if you do what you've just done, and you ask, what is the tunneling rate from the ground state, not from the bottom of the potential, you get a different result than Coleman's, apparently. But the kind of fun thing is, if you, the kind of fun thing is, if you then expand that result in a ratio of the false vacuum energy to the energy of the barrier, you actually come back to Coleman's result. So I'm sort of saying that sometimes if you do tunneling from the state rather than from the bottom of the potential, you actually get an equivalent answer both ways. Does that make sense, or could you have some comment on that?
Yeah, so in the okay, what I can say about the ground state in this particular picture is that the people who came up with this direct approach, see the paper again? Yeah. So their argument, which I never explicitly checked because I trust them, was that you start from that they assume they assume the ground state to be some very localized wave package with all of the within this initial sloshing, basically just shrinks down to approximately the false vacuum state. So not really also the ground state the ground state in this case would be the lowest resonance state. And it is to some extent, of course, an approximation to think about the false vacuum as that false vacuum. Okay. It is not, yeah, you're right that of course the lowest energetic state that you can have in this false vacuum basin, which would be the lowest resonance state, is not the same as just the bottom of the potential. And I think normally one makes the approximation that those are the same, but they are different. And I would guess that if you want to, in the path integral formalism, actually get some resolution on the spread of your lowest lying resonance state in the false vacuum basin, you would have to use this framework because
Yeah.
you don't
So what I'm saying is, if you use a framework like yours, you actually get back to Coleman's result as if you started off from the bottom of the well. Something that used to worry me, but actually it turns out the two approaches give the same answer when you work them out in detail. Which is not obvious, far from obvious. In fact, in Coleman's original, I think Coleman was originally very influenced by an earlier paper by Bender and Wu on tunneling in a system with two dimensions, two fields, two particles. And he misquotes Bender and Wu because he actually quotes their result, but their result is tunneling from the ground state, not from the bottom of the potential. And it's kind of fun to go back to read some of these original papers and see what the thinking was at the time.
Yeah, I agree. Okay. Good. So I guess this concludes this session. Thank you again, everybody, for joining in. Thank you, Thomas, for the very clear presentation. And I guess I'll see you in about a month's time. So May 22nd is the next talk. So see you there. Thank you, everybody. Bye.
Excellent. Thanks a lot, Thomas.